Right, welcome back to another video. Now, this video is about force and elasticity. Now, when we stretch a spring, we put a weight on a spring, the spring stretches. Now, suppose the spring had an original length L0, L0, and when we put the weight on it, it stretches to a new length L. So by how much has the spring stretched? By how much has it extended? Well, it has extended by an amount E, which is given by L take away L0. So the extension of the spring, E, is equal to L minus L0. Now, suppose originally the spring was 10 centimeters long. If this was 10 centimeter, and when I put weight on it, it extends, this is 10 centimeter. This one stretches to, say, 12 centimeter. Then the extension is going to be 10 take away 12. Like this would be, 12 take away 10, which is 2 centimeter. Okay, so we can work out the extension. Now we can do an experiment. Okay, you take a spring and you put different weights on it, and you got a scale here where you can measure the extension. Now this is a standard experiment that we do. Now suppose if I put a weight of 5 Newton, the spring stretches by 0.1 meter. Now we're going to use meters and Newton, which are the SI units. Now, if the weight is 10 Newton, it stretches by 0.2 centimeters. Now, it's stretching equally for equal weights, which means the extension is directly proportional to the force that we apply. Now, does that keep on happening? Now, if I keep increasing the force, it will keep on stretching and keep on stretching. Now, when we remove the weight, it will go back to its original length. Now, if it does that, we say that the spring is within its elastic limit, or the limit of proportionality, where the force is directly proportional to the extension. However, if you keep on loading it more and more and more, until a point will be reached where the spring becomes permanently stretched and it no longer goes back to its original position. And we call that limit the limit of proportionality, or the elastic limit. So suppose when the spring reaches this point, and if I put more weight on it, it will extend by more amount with less weight. So what happens is the graph tends to go in this direction, like that. Okay, so even with less weight, we are getting more extension because the spring has become deformed and it stretches more than it should be. So we call this point L. L is the elastic limit. Okay, so we call this the elastic limit. Or the limit of proportionality. Okay, now up to here, the weight is directly proportional to the extension. However, after that, it's no longer proportional. Okay, so what happens is if I unload it from this point, if I unload it, you'll find that it will not return back to its original length. and the graph will, on the way back, the graph will probably look something like this. When I'm unloading it, okay, it will become permanently stretched by, say, 0.1 meter, which is 10 centimeters. So, no, this relationship is expressed in using Hooke's law, which says that the extension is directly proportional to the force, provided the elastic limit is not exceeded. So up to this point, from 0 to L, it is within the elastic limit where the Hooke's law is obeyed. Now, if we load it more than that, if I increase the load more, the extension becomes greater and it no longer obeys, and the spring becomes permanently stretched. Now, we can say force is directly proportional to the extension, E. Now, F, to change a proportionality into an equation, we have to put a constant of proportionality, K, where K is, we call the spring constant, and it has a unit of newtons per kilogram. And we can find this spring constant by finding the gradient of this graph. Okay, so if I take 2 points on the graph like this, these 2 points, then the gradient of the graph will be given by this, which is the force. So force goes from 5 up to 20, that's 15 Newton. Okay, and the extension on this side from 0.1 to 0.4, that's 0.3 meters. So it extends 15 newtons, it extends 0.3 meter or 30 centimeter with a force of 15 Newton. So we can work out this constant, K, so we say, I'll write this in red, K equals 15 divided by 0.3, 15 divided by 0.3, which is 50, which comes to 50 newtons per meter. Okay, the unit of the spring constant of this spring is 15 newtons per meter. Now, what does that mean? It means the spring stretches by 1 meter with a force of 50 Newton. So you need 50 newtons to stretch it by 1 meter. Now, what happens if the spring was stiffer? So if the spring was stiff, the graph will go something like this. It will have a steeper gradient. That means it needs more force to stretch it by a small amount. Okay, so here we can say this is stiff. Now, if the graph went down this way, that means the spring is much softer. Okay, so the spring constant tells us how much force is needed to stretch the spring 1 meter by 1 meter. Okay, the next thing that we're going to talk about is energy. Now, here, just to complete this, you'll find that force divided by the extension, this is force, this is the extension. Now, if you divide 5 by 0.1, that gives you 50. Okay, 10 divided by 0.2 is also 50. So the answer here is constant, is 50. So we say force divided by the extension equals a constant. Okay, and this one is, and this is that constant that we worked out here by the gradient. Okay, uh, energy stored in a stretched spring. Now, the formula for energy, I'm just going to give you the formula, okay? We don't need to derive it. Energy stored in a stretched spring, E. E is equal to half times the constant times E squared. Okay, so you just need to know how to use this formula, where K is the spring constant, E is the extension. So energy is equal to half Ke squared. Now, if we use the same spring, if the above spring, the one we talked about, okay, was stretched, is stretched by 30 centimeter, by 30 centimeter, what is the how much energy is stored in the spring? I can let this bit out. I'll leave that for the time being. Okay, if the above spring is stretched by 30 centimeter, how much energy is stored in the spring? So we can use the formula. Energy is equal to a half K E squared. Now remember, the spring constant is 50 newtons per meter. So we say half times 50 times the extension is 30 centimeters. Now remember, this constant is given in newtons per meter. So we need to convert the unit into meters. So we say 30 centimeter. Divide that by 100, that gives you 0.3 meters. Okay, so we have to use 0.3 meters. That's 0.3 all squared. And if you work that out, the energy comes to 2.25 joules. Now, remember, how do we use this energy? Like for example, you have a bow and arrow. Okay, so if you stretch a bow, suppose the elastic band of the arrow had this much energy stored in it. Okay, and when you fire the arrow, you stretch the elastic band and you let it go. All that energy is converted into kinetic energy of the arrow. Okay, we can work out what if this energy was given to the arrow. of mass (100 gram), what is the velocity of the arrow? What will be the velocity of the arrow? Okay, so remember, if this was a spring or an elastic band of the arrow, and when you stretch it, you store that much energy, and all that energy is converted into kinetic energy of the arrow. So we say that the elastic potential energy is equal to the kinetic energy of arrow. Now this is the energy that is stored in the spring or in the elastic band, which is 2.25 joules, is equal to kinetic energy of the arrow is half. Remember, the formula for kinetic energy is half mv squared, half times the mass. No, remember, the mass has to be in kilograms. So we're going to convert 100 grams. 100 grams is 100 divided by, that's 0.1 kilogram. And that will give us the velocity in meters per second. A half times 0.1 times the velocity squared, v squared. Okay, now if we rearrange the formula, take the 2 on the other side and multiply. So we say v squared is equal to 2.25 times that by 2. Now 2 is dividing this side, so you times it. Then you bring the 0.1 on the other side. 0.1 is multiplying. So if you divide by 0.1, you divide this side by 0.1. That will give you the square of the velocity. Now this comes to 45. So v is equal to the square root of 45, which comes to 6.7 meters per second. Okay, so the arrow will move off with a velocity of 6.7 meters per second. So this is a good example of conversion of energy from one form into another. In this case, the elastic potential energy of the stretched elastic band is being converted into kinetic energy of the arrow, and which gives the arrow this velocity.